Hello students, welcome back. The final topic here is the logistic model. This is an important application and it is being used in a lot of different fields like population growth in a closed environment or disease spreading around in a society, epidemic model, or rumors spreading around in social media and so on and so forth. It goes like this: let P be population, then the rate of change is proportional to this quadratic expression of the population. Here's a visualization. So this quadratic expression is concave down like this. That's because of this minus sign here. And when population is pretty close to 0 around here, then because this is pretty close to 0, the rate of change, the derivative is also pretty close to 0. So what do we have around here? We have relatively slow growth. Around here, on the other hand, around the mature population, this is close to 0, b minus p. Therefore, this part is close to 0, therefore what? The rate of change is also pretty close to 0, and we have, again, very slow growth. In the middle, on the other hand, this whole quantity is large, therefore we have quick growth here, fast growth. That's the kind of situation we are going to be faced upon in any kind of epidemic model, as a matter of fact. Disease is spreading around. Early on, you hardly notice. And then in the middle, we have explosive growth. And then later on, it'll stabilize, herd immunity or things like those. But then again, by that time, tragedy already struck. In any case, that's what we are modeling here, the logistic equation. Here, the constants A and B are positive constants, and they're related to the environment or the species or the virus itself, those kind of things. Let's go to the solution. The typical technique we are going to be using is, number one, separation of variable. And that's the easy part. We apply the separation of variable, p times b minus p, flip it over to the other side as denominator, and then we take the antiderivative of both sides. Here, I could have left b in the right-hand side as denominator, but I decided to put it over there. The reason I did this is because the computation becomes a bit tidier if I do it this way. Okay, and then how do we calculate this integral here? The right-hand side is easy. The left-hand side, that requires a little bit of work. It turned out this fraction is equivalent to 1 over p minus 1 over p minus b. How is that? Well, let's check. 1 over p minus 1 over p minus b. And then let's take common denominator, p minus b over p times p minus b minus p over p times p minus b. I just took the common denominator. And then what do we have? We have p minus b minus p in the numerator, and then the denominator is p times p minus b. Do you see cancellation? Of course you do. This minus p and that p cancel each other out, and we have minus b over that. And then let's change the sign. B over p times b minus p. And that's precisely what we have over there. So yes, this is correct decomposition by partial fraction. We just checked it. Now let's take the antiderivative. Let's color this one in blue and let's color this in red. So we have log of p minus log of p minus b is equal to a times t plus some constant c. Okay, did I do everything correctly here? By the way, this came from blue and that came from red. I guess that's clear. All right, anti-differentiation is done and we got the implicit solution, but we are far from there. We want the explicit solution. And how do we get there? We have to solve for p and they're inside of the logarithm, so we'll have to remove it. It's hard to remove them if we have two logs flying around. So let's combine the logs. Log of p over p minus b, and we can always do that because of the log rule, and that's equal to at plus c. And then we can take the exponential to remove the logarithm. P over p minus b is equal to exponential of at plus c. Is everybody happy with this computation here? Okay, this computation is okay, but there's a bit of a problem here. What if p is negative or p minus b is negative and so on and so forth? Can we handle that? Yes, we can. The typical trick is to decompose this exponential like this. And e to the c power is a constant, and let's name it to another character, like k times e to the a t, like this. Now we can allow k to be negative so that we can accommodate p being negative or p minus b being negative and things like those. We discussed this already in real utmost detail before, so I'm not going to dwell on it too long, and let's go from here. So we don't have logarithm anymore, and we have some algebraic equation of p to solve. Let's go ahead and do that. p over p minus b is equal to k times e to the a t power, and from here let's solve for p. How do you do that? Well, don't be intimidated by this exponential and all. This whole thing is just one expression, and this is nothing more than a linear equation as a matter of fact, linear fractional equation. Just remove the denominator to the other side, flip it over, k e to the a t power times p minus b. And then break out the parentheses. P equals to p times k times exponential of at minus b times k times exponential of at. Just broke off the parentheses. I'd like to have just a little bit of space here. Okay, all right. Okay, did it improve? At first glance, you may not see it, but it did improve as a matter of fact. What we can do is bring this p term to the other side and get all the p's in one side and everything else to the other side. This is what I'm talking about. P minus p times k times exponential is equal to negative b times k times exponential of this. Did it improve? Do you see it now? We have p and we have p here as well, so I can factor p out. So 1 minus k times exponential, and that's equal to negative b times k times exponential. So here, from this equation, we're actually foreseeing this already. Why are we moving this denominator to the other side? Well, that's actually natural. Whenever you have denominator, usually it's better to remove. But then, why do we break up and why do we move p term to one side, everything to the other side, and do things like those? Because we want to do this. Get all the p's in one side, everything else outside here, and then factor p out, and we have only one p here. Here we had two p's, now we have one p. All you have to do now is to divide by this, and I'm going to get the solution. So p is equal to negative b k e to the a t power divided by 1 minus k exponential of a times t. There you go. We have an explicit solution. However, we can do a little bit better. There are too many exponentials flying around, too many t's, so let's simplify this a little bit. Divide each term by negative k e to the at power, then I'm going to get p equals b over, and then negative 1 over k, and then e to the negative a t power plus 1. That's what I'm going to get. Let's see. I divided, I need even bigger font here. Okay. I divided everything by negative k e to the at, so this whole thing becomes plus 1 here, all right? And then I divided by this thing, including negative sign, so I have only b. And down here, by trade-off, I get something complicated. I divided, so I have e to the negative at power, and then we have something complicated here, but that's okay. K is a constant to be determined. So why don't I simply name it something different? Instead of negative 1 over k, let's name it as some other character. Let's call it small c. And there you go. This expression is a final form, the general solution that we want. Of course, you could call this one as general solution too, of course. It's an explicit expression, but some simplification later, this one looks better. What answer can you derive immediately from here? When t is really big, then we have t e to the negative infinity here, so that goes to 0, so this entire thing drops out, and what do you get? P of t will approach the b, decimal tooth population we are talking about. What if t is going to negative infinity, then this is e to the positive infinity, and that's infinity. Denominator is getting huge, so this entire thing is going down to 0. That also fits our common sense. Any question about this solution here before moving on? Separation of variable, and then integral computation was a bit trickier this time because we had to do the decomposition by partial fraction. And that gave us that implicit solution, but less so for p. So take those two logarithms together as a single logarithm and take the exponential, and that'll give me this linear fraction p over p minus b equals to this exponential, and we are solving for p. Move the denominator, break up the parentheses, take all the p terms one side, everything else to the other side, factor p out and divide, and then we get what we want. Okay, they're all done. Here's the explicit solution. And then let's go to some example problems. Here are some leftover problems for students. Oh, I already talked about all these. Okay, never mind. Let's go to initial value problems associated to those logistic modeling here. Okay, we have general solution here, and we have to use this initial condition and then solve for p. I'd like to save some time, so let me show you the answer here. So general solution is here, okay, and then plug in t equal to 0, that's equal to b over 2, so we have this equation. C to the 0 power is e to the 0 power is 1, so c equals to 1 here. Therefore, we have this solution here, b over 1 plus e to the negative at power. And then if you take the limit as t is going to infinity, then we have that mature population there. Here's a visualization. Grow slowly and then explode, and then we have stabilizing mature population. And this is better visualization as a matter of fact. Let's go down a little bit so that we can see the picture a little bit better. Okay, look at the arrows. Follow the arrows, and we have increase, but slow increase, but explode, and then eventually stabilizing into mature population. How about the next problem here? B is the mature population, so we are starting with a population higher than the mature population, so the population will go down and stabilize. How do you actually get that? We have the general solution and then plug in and then find out C value and so on and so forth. I'm going to leave that to students. I'll just show you the picture. And this is what you're going to get. You begin from higher than mature population and come down, 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 and stabilize. The last question here is kind of gimmicky because we have negative population. That doesn't happen in real life situation. If this had been some modeling problem, this never happens. But this is a math class, and just for math class exercise, it is conceivable. And again, you can do these kind of things. You see, plug those numbers, this initial condition into the general condition here, and then solve for C, and you can do that. And I'm going to leave the details to students. And then if you superpose it to direction fields, this is what you're going to get. Negative population, just go down to negative infinity. And how about this part? This part is completely unrelated. So this limit is invalid because we cannot go to infinity. Before going to infinity, the system goes down to pit. So everything breaks down before going over to infinity. Okay, that completes my presentation on logistic model. Now your job is to think about how to apply it, how to get data and use this logistic model. Think about that. I may give you an appropriate project on it.